All right. So the other day we started talking about complex numbers, right? And so fundamental theorem of algebra was that basically all functions have roots. Even if I got a function like x squared plus 1, what's a root? Where the function touches the x-axis, where it crosses through 0. Does x of t here cross through 0? It doesn't, right? So, but we still say it has roots, right? And we basically said for this guy, I set where this is equal to 0, I get x squared equals minus 1. So that says x equals plus or minus the square root of minus 1, which you were told had no meaning, but we call that j, or the imaginary number, right? I is what you would have learned in high school. All right, j is what we tend to call it because you're going to see situations like in 2112 where you say that the current I equals 3 plus 2i, right? That looks like an algebra expression. So we use j to represent that it's not current, all right? And it's really useful. I talked about this the other day because there's a relationship in general between sine waves and complex numbers. The example I gave, as I said, if I had that voice signal, we looked at this. If I had a voice signal like this, it's a sum of sine waves, all right? It's a sum of sine waves. If I was processing that voice thing, let's say I want to do some AI and I want to be able to learn or do some speech recognition or something like that, something that's going to require some advanced work, right? One of the things that we ultimately need to do is to figure out, we said, what frequencies, what sine waves are in there. When I say what frequencies, what do I know? I know that what I have with this thing is a sine wave has, some of you guys have already forgotten about this. If I said just in general, how do I write cosine as a function of time in general? Omega t plus some phase shift at t equals 0, right? So I've got that general expression. So really what I want to know, if I want to understand what sine waves are in here, I guess I should say I got one other thing. I got an amplitude on it. What this graph here tells me is basically what frequencies are in this waveform, and the y-axis value tells me what the amplitudes of them are. How big are they? Right? It's fundamentally what that thing's telling me. And I said, it's really hard to do math with cosines, and you probably are sort of know this, or you should know this. Differential equations are really frustrating to deal with. You may like differential equations or whatever, but if I had to solve circuits every time that had resistors, capacitors, and inductors using differential equations, it would be a nightmare to solve everything, right? And so what do I have to do? What I can do is I can use complex numbers to simplify that process. So what I talked about the other day is there is a process by which we can think of those sine waves as complex numbers, ultimately as e to the something times I, right? I, the complex number, what I'm going to call j. What that does ultimately, again, this may not mean a whole lot to you yet, but if I look at in signal processing, where I'm trying to play with those sine waves, example I gave was if I want to analyze that sine wave and figure out what frequencies are in it, if I had, I'm getting too far ahead of myself in saying this, but if I had basically 1,000 points in that sine wave, which is not a lot, okay, you're going to see this when you get in the project. You're going to have much. If let's say I had 1 second or 10 seconds worth of audio, there'd be a lot more than 1,000 points in that audio, right? You're going to see that. It's probably going to be 1,000,000 points or something in that audio, right? What's going to happen is processing that. This is the number of multiplications that I have if I want to process that. 1,000,000 multiplications versus if I use complex numbers instead, I can have 5,000 multiplications. That allows me to really start to speed up all the processing and everything that I do. So from a computer engineering perspective, right, it's really useful for me to be able to understand how to deal with complex numbers because it allows me to do a lot of the complex processing. Complex in the sense that we're using the word complex here a lot. I can use imaginary numbers, I'll say it that way, because it simplifies a lot of the processor work that you would have to do, right? So we need to be able to understand that concept. All right. So the other day, right, let me make sure it's okay. All right. So the other day we introduced this idea. I basically gave you a couple of different forms of the complex number, right? So I said I got R equals A plus JB, and I show that in what I call the complex plane. So it's an XY axis system. Got a real and imaginary, where the imaginary is the y-axis and the real is the x-axis. So normally I say that's A plus JB. So A is the real part. So let's say I do that and I say R equals A plus JB. You guys tell me, what is the real part of A plus JB? A. What's the imaginary part of A plus JB? B, not JB, right? J is like the unit vector that you would have when you're looking at vectors in physics. Okay. All right. So in this case, we basically said I can look at this thing. If this is the vector here, this is R. Now, I usually draw that with a little underbar like that. All right. That's what's typically done for these things in complex numbers. I can think of this as just a right triangle, right? So the magnitude or the length of it is that. I write the length with the absolute value sign. And the angle of this guy is this, right? So I'm looking at this as a right triangle. And so typically, when I look at this, what we did the other day is we used basically our trigonometry to say, all right, so if I have opposite over hypotenuse, what is opposite over hypotenuse equal to in trig? The sine, all right? And so that's how I could figure out the imaginary part and the real part, all right, was using some basic trig. Now, the other thing is here is, what if I wanted to figure out that length, the magnitude of that vector? How would I figure that out? Knowing A and B. So if I know this length, A, the real part, and I know that length, B, how do I figure out? Pythagorean theorem, right? Square root of A squared plus B squared. Okay, and we went through, MATLAB has an approach to be able to do that as well. So we went through this the other day. One way that we often, if we know the real part and the imaginary part, so if we know A and B, if we know these two values, the other thing that we said that we do is we use the tangent of that angle, right? Now, the problem that we run into is when I know B and A and I want to figure out phi, right? So let's say I know B and A and I want to figure out phi. So if I know that, how do I figure out phi? Arctan, right? Or inverse tan of B over A is equal to phi. Okay. All right. So when we do that, what's the problem with that potentially? What do we say about arctan? Well, that's about, yeah. So 90 degrees goes to infinity. Negative 90 goes to infinity as well, right? So you see, yeah, it only exists between what points? Between negative 90 and 90. And it doesn't exist at negative 90 or 90 either, right? So if I'm over in the what quadrants is this a problem then? If I'm looking at my complex plane, where do I have angles that are not between negative 90 and 90? Which ones? Second and third. So number 2 and number 3. So over here, right? This is to this is the 90-degree line. This is the negative 90-degree line. So everything from here over is between negative 90. So let's see. Everything over here is basically theta between, I guess I'm calling it phi here. Phi between what? 90 to 270. Which again, we usually think of angles in this half. So first and second quadrant, we usually think of those being between 0 and 180. Numbers between, or any vector between in the 4 and 3, we usually think of as having an angle between 0 and minus 180. You could also say it's between 180 and 360. Totally fine. But generally speaking, we tend to do it so that it's positive in 1 and 2, and it's negative in 3 and 4. Okay. What if I gave you the number negative 1? Okay, negative 1. How do I write negative 1 in polar form? So real quick, polar form, that was the other way to talk about this, right? The other day I ended with 3 forms. One was the Cartesian, A plus JB, or rectangular. The other is R, the length, with the magnet or with the angle. Okay. That's the polar form, the length with the angle. If I give you the number -1, how do I write -1 in polar form? Well, let me ask you, if I have a magnitude, is -1 a magnitude? Well, -1's kind of a scalar, I guess, right? But this has a directionality to it, right? So the magnitude is a length, an absolute value. I can't say the length of this is -1. I'm treating it like a complex number. I'm saying it's a complex number. All complex numbers can be thought of as a length and an angle. So the number 1 is a complex number, right? So we look at the world of numbers, right? You guys learned how to count, right? So at that time you learned whole numbers. Then you learned that there were integers. Then you learned that there were decimals and all that sort of stuff. Basically, what you think about most of the time is real numbers. Real numbers are basically everything from negative infinity to positive infinity, right? What I'm really saying is the whole universe of numbers is actually numbers that live not on the number line, but on the number plane. All right, so if I have a complex number, it can be thought of as having a magnitude and an angle. So let's take 1 and -1. How can I write 1 as a complex number in polar form? You could do it that way. I could say 1 is equal to 1 plus j 0. Right. So I could say that that's 1 angle 0 degrees. Or where we ended the other day was with this notion of using complex exponentials. Right. I'm going to come back to that. I don't want to get into that just yet. Right. How about -1? What's the length of -1? 1. Angle 180. Or -180. It's the same thing. All right. I could use both. Right. Sometimes people forget that. Right. Like if I tell you that I have ultimately -2 cosine 3t, what would you tell me is the amplitude of -2 cosine 3t? The amplitude is 2. All right. This guy has a phase shift ultimately of 180 degrees, which is something we'll talk about a little bit more. All right. But basically, this is something to remember. All numbers have an angle like that. All right. So there's a summary that I give you kind of in the notes, and we went through a couple of examples of this last time. What I want to do is I want to pick up with where we were last time. So I ended with this notion of Euler's identity. All right, which is to say that if I have a vector, let's look at it this way. If I've got a vector R, right, R can be thought of as A plus JB. It can be thought of as a length with an angle phi, or it can be thought of as A plus JB can be related to the length and the angle by saying it's length cosine phi plus J times length sine phi, right? That relationship, this is the Cartesian. It's equal to that in polar form. Because of the trig relationships, I can write A plus JB like that. And I said there is this other magical thing called Euler's identity, which we're not proving, which says e to the j theta equals the cosine of theta plus j times the sine of theta. All right, you can look at the proof of that in the book. It comes from Taylor series expansion. Not going to go into it. Basically, we say this becomes the magnitude of r e to the j phi. All right, and I can make those relationships right there happen pretty easily. Right. All right, that's really the core of most of this stuff. Now we got to play with it and use it. Okay, so we ended there the other day. I said, what's useful about the exponential stuff, right? What did I say about, like, if I have e to the a divided by e to the b, what is that? Yeah, e to the a minus b, right? So it allows me to do multiplication and division pretty easily. All right, so this was what we talked about last time. We went through a couple of examples. So I basically said, what if I've got 3 angle 45 and 4 angle -90? All right. Real quick, just to see if we can remind ourselves of this. If I've got 4 angle negative 90, how can I write that in polar form? Or sorry, not that is in polar form. How do I write that in rectangular form? Four cosine negative 90. Okay. Yeah. So 4 cosine negative 90 plus j times 4 sine negative 90. Okay. What's the cosine of 90 or negative 90? 0. Okay. This guy would end up becoming negative 4j if you did that math. Okay. All right. So j and negative j tell me that those numbers have angles of 90 or negative 90 respectively. All right. You'll get used to tracking that stuff. All right. So all right. Where I ended up with the other day is so I used this example, right? What if I had these two numbers here? All right. So Z1 was 2.1213 plus J 2.1213, and Z2 was equal to 2J. All right. What I went through last time was I calculated that these two things, Z1 was equal to 3 angle 45 degrees, and 2j was equal to 2 angle 90 degrees. Was where I ended up. Okay. So what I did was I did some calculation. I said, let's say I want to calculate Z3, which is Z2 divided by Z1. All right. So what I did was I divided their magnitudes and I subtracted their angles. Let's say I want to calculate Z4, which is Z1 times Z2. So let's say Z1 was equal to, what did I say? 3 angle 45 degrees. And Z2 is equal to 2 angle 90 degrees. So what do I do to get those two guys multiplied together? Multiply the magnitudes, add the angles. And again, I go back to the fact that these are just in Euler's form. All right, get me to the Euler form. Right, so if I have 3 angle 45, that's the same as 3 times e to the what? E to the j 45 degrees. And then for Z2, it's 2 e to the what? E to the j 90. So what I'm saying is I got 3 e to the j 45 degrees times 2 e to the j 90. Right? So I basically end up with 3 times 2. And then I have two exponentials that are multiplying each other, right? So what do I do with the exponents on those? Yeah, e to the j, what? 135. Or I can write that as 6 angle 135. How would I get that into rectangular coordinates if I wanted it that way? Because that's the stuff I'm going to do on the test. I'm going to say, give it to me in rectangular coordinates. So you probably should do the work this way and then convert. How do I get that to rectangular? 6 cosine 135. 6 cosine 135 plus j times 6 sine 135. Like that. Okay. All right. And I'm just using trigonometry to make those conversions. And then you can figure out cosine of 135 is, I don't know, there's a square root of 2/2 in there or something, right? I'm not too worried about that. This is the key thing that I want to make sure that you can do the conversion of. All right. Now, where I ended the other day was I said, well, if I put this stuff into MATLAB, right, to let MATLAB do it, MATLAB can't, you can say 3 plus J2, right? You can tell it that, right? I cannot tell it polar form, right? So what it does is I got to use this Euler form. So what I did here is I said 3 times exponential, that's the exponential function. MATLAB recognizes j as the imaginary number. So I said 3 times j. Now what is that there? 45 times pi over 180. What did I do? Degrees to radians, right? I took 45 degrees and converted to radians. Why did I do that? Because I'm a dork and I like radians. I actually hate radians. What's that? MATLAB can only recognize radians, right? But it's because honest to God, math definition of all the trig functions is defined in terms of radians. And so exponential is a trig function. All right, you didn't know that, but it is. All right, because of this relationship. So when I want to do the math, I got a summary of these things here, right? But basically, MATLAB has a function called angle, and it's got one called abs. Abs tells me the magnitude, angle tells me the angle, and it's smarter than the arctan function. What's it mean that it's smarter than the arctan function? What would we say was the problem with the arctan function? Undefined in quadrants 2 and 3. All right. So some of you are going to mess up for sure on the test on those questions. All right. But if I use the angle function, it gets that right. All right. So you have to think about where those are. So let's try to do this. I said I want to do Z1 divided by Z2 for these two numbers. Z1 is negative 3 plus 6J, and Z2 is 4 minus 3J. Okay. And I want to do Z1 divided by Z2, and I want to do it in rectangular format. How do I do this? How should I do Z1 divided by Z2? Convert to polar or complex exponential. All right. So how do I do that? How do I get the magnitude of Z1? Square root of A squared plus B squared. So that's simple, right? Minus 3 squared plus 6 squared, right? Whatever that is. I'm not going to calculate it right now. What's the magnitude of Z2? Square root of what? 4 squared plus what? Plus negative, yeah, plus negative 3 squared. Now, the key thing is it's not negative 3J squared. Some of you are going to do that. What's the problem with that? No, that's not the imaginary part. What's the J? The J is like a basis vector, like a unit vector when you're dealing with physics. What's J squared? Negative 1. All right. So if I included that in there, I'm going to totally get the wrong answer, right? It should be negative 3 squared. Negative 3 squared is what number? 9, not negative 9, right? If I had put negative 3J squared, I would have come up with negative 9. Right? That is not at all going to give you the right answer for the length, right? So, all right, so I've got that approach. How do I get the angle of these things? Let's say I want to get the angle of Z2. Let's start with Z2. How would you get the angle of that? Take the arctan, right? Arctan of what over what? Well, if I can't remember, what I always do is I draw it. So 4 minus 3J, where does that guy sit? Which quadrant? Fourth, right? So over 4, down 3. So he's going to be somewhere like this. All right, this is Z2. So the phi I'm talking about is basically there. Okay. All right, so I look at this, it becomes tangent of what over what if I wanted to get that angle. Imaginary over real. So that's negative 3 divided by 4. Right? Because the imaginary part's negative 3. It's not 3, it's negative 3. Okay. All right, now what about for our friend Z1? What do I do for him? What's that? All right, so you can see the arctan of 6 over negative 3. I have to take into account the fact that it's over in the other two quadrants. Where is this guy? Which quadrant? 2. So over 3 up 6. So he's basically like that. All right, this is Z1. It's useful to draw them so that you don't fall into the trap of just taking the arctan of B over A. Right? Because this guy, that won't work. I have to add 180 degrees to whatever that's going to be. Right? I could also subtract 180 degrees and get an answer that's correct. I have to take into account that it's over on the other side. All right. So we looked at that the other day. All right. So if I want to do now Z1 divided by Z2, it's fairly easy. I just say Z1 divided by Z2 is whatever that magnitude is, divided by whatever that magnitude is. And then I say it's the angle of Z1 minus the angle of Z2, and I'm good. All right. That's the approach that I get. I can take that result and convert that result now back to rectangular if I want to solve that problem completely. Now, how did I do this in MATLAB? I want to take a look at that. What did I do there? Clear all. What did I do with the clear all? Clear out basically all my variables. Now, again, you don't have to do that when you're in the web browser MATLAB. The reason you don't have to do that in the web browser MATLAB basically is because it automatically runs that for you, and it gets confused if you do it a second time. When you start writing scripts, and you may not be doing that now at all, but again, when you get to the project in a couple of weeks, you're going to be all script based. It's all going to be you on your computer dealing with it. So if you don't make the clear all, you're going to run into problems. All right, so I did Z1 and Z2 there, -3 + 6j, 4 - 3j. Then what did I do here? So I did a couple of things, right? So I wanted to show 3 ways to compute the magnitude. All right, the way that I do it normally is I use the abs command. Abs takes the length of a vector. All right. Now, the other thing I did was I did it basically the old school way. Square root -3 squared + 6 squared, what we just did. What am I doing here? Well, I'm using the real command and the imag command. What do you think they do? One takes the real part of the number, one takes the imaginary part of the operator. Those are operators that we have. So if I say real of Z1, what do you think I get from that? -3 is what's returned. Imag of Z1, what's returned? 6. All right. Now, why do I like this line here and not that line there? I want you to know line number 2, but I don't like line number 2. What did I do with that?
Because you can change the variable.
I hard coded it. Yeah, when I hard code stuff as a coding practice, hard coding is stupid. You guys do it all the time, right? And you'll continue to do it because it feels easy and it's the way you're used to thinking, right? The problem is I might change Z1 up at the top. And then if I mentally pulled out values of Z1, I might think I changed something, but I probably didn't, right? And then you end up searching your code for an hour to figure out where your problem is. You want to keep stuff in variables like that and use functions like that as much as you can. That's the way you normally write code. Or else you end up tracking problems forever. All right, so I'm showing you that just to get you comfortable with MATLAB, but also just to get you comfortable with like the general process of how one should be writing code when you're writing it. Okay. All right. So then I also did down here, all right, 3 ways to get the angle. All right, so again, what do I typically do? I did angle Z1. What did I say was smart about angle? What's smart about that function? Rather than using this, so MATLAB ATAN is the arctan. What's smart about that?
You don't have to use the +180.
I don't have to use the +180 thing that I did there. Now, what did I do? In other words, I don't have to think about what quadrant it's in. Angle just takes into account what quadrant it's in, right? So it's got some code built in that does some checks, and there's probably an if statement somewhere in that thing, right? Now, what's going on here? What did I do again? What's the 180 over pi? What do I know is going to come out? Angle is a trig function. So what's the result going to be in? Radians. I did 180 over pi. Why do I do that? Because again, most engineers, when you're talking in terms of degrees, like if I work at Duke, we'll be talking about voltages throughout the distribution system, right? So I might be saying that what's the angle of the voltage, right? No one at Duke, when they look at the distribution center, no one's going to say that the angle of the voltage is pi radians, right? They're going to say it's 180 degrees. Okay, so generally speaking, I'm going into degrees rather than radians. All right. So, how did I do the math on everything? This is basically, again, you can look at this in some more detail here. So Z3, when I did the division, I can separately do the math on the magnitude and the angle. And then what did I do here? Well, I recomputed the real and imaginary part using basically magnitude times cosine of the angle, magnitude times sine of the angle. What's deg to rad? I put all kinds of different functions in here. What is deg to rad doing? Degrees to radians, right? MATLAB also has a function I introduced the other day, which is in my summary, which is cos D and sine D. What do those do? Those are degree versions of cosine and sine. All right, so sometimes I use those functions. All right. What's this? Z3 equals Z3 mag times that whole thing. What did I do here? Yeah, so this basically this is the Euler's form sort of thing. So I'm saying it's the magnitude of Z3 times e to the j angle of Z3, whatever that is. Okay. Now in MATLAB, it never writes it. In other words, if I looked at the output of this on the screen, it's not going to say a magnitude and an angle. Any complex number, MATLAB's always going to write out in rectangular form. If you want the angle and the magnitude, you got to compute it. All right, it will never give it to you. It'll never spit it out directly. All right, by default, it does it in rectangular form. So if I wrote this out, it would tell me A plus JB, whatever A and B are. Okay. All right. So if you were really wanting to do this and you were being lazy, I'd say Z3 is Z1 divided by Z2, which is the exact problem I gave you before. And I would have written in Z1 was whatever I told you, and Z2 is whatever I told you. Take the real and imaginary part and you'd be done. Right? I could do it that simply. In fact, I don't even really need to do that. I could just type in Z1 and Z2, do this, and then look at it on the screen. That would be in rectangular form, and I'd be done. Now, you should know how to go through all the different steps that we just went through. All right, in terms of the way you can do the calculations. You should be able to do all the calcs by hand, but I would expect that you also get comfortable using the tool like this. All right. All right, let's for any questions about this, right? There's just a lot of different stuff to keep track of, but it's really not that hard. At the end of the day, it's just trig, really. All right. Imaginary numbers seem weird, they're helpful, right? And it's really just trig to be able to play with them. All right. Conjugates. If I have a conjugate, some of you may already know a conjugate. Let me just write this off to the side. Let's say I have Z1 equals 3 plus J2. A conjugate, I write a Z1 star like that. That's a conjugate. So it's a useful operation that we use a lot. Anybody know what that is? Yeah. Change the sign on the imaginary part. So it'd be 3 minus J2. All right. Now it turns out why is that special? Why isn't minus 3 plus J2 special? Right? This is special in part because if I take a I think, let's see, if I did this and I said, what are the roots of that thing? What are the roots of that thing? Yeah, that wouldn't, I want something that's going to be, well, heck, let me just even take this one. X squared plus 1 equals 0. We know that X equals plus or minus J. What are those two things using this term conjugate? Well, they're conjugates. What's going to turn out is anytime I get roots of a quadratic, one root is going to be 3 plus J. There's one root will always be A plus JB. What will the other one always be? A minus JB, right? The two roots of a quadratic are always going to look like that. So this conjugate thing is important. That's why we refer to it. And we use it a lot. It's not that big of a deal, but basically what I say is R star here, the conjugate of R, is A minus JB. And the other thing is basically its angle phi is the opposite, right? So if I have R up here, this guy down here is R conjugate. He's got the negative angle, right? So if this angle here was, I don't know, looks like it's about 60 degrees. This angle is what? Negative 60 degrees. Okay, so that's how they relate to each other. All right. We're going to use that. I have that, I know, in the last problem or second to last problem on the homework. All right, let's say I got this guy. 1 plus 2j to the 8th power. How should I do that? Any ideas? the Euler's form, right? So let's say I had, e to the 4 raised to the 4th power. What's that? E to the 16, right? So what am I doing here? I'm saying, well, I want to figure out what this guy is. So 1 plus 2j. I want to get that into the polar or the Euler form, right? So 1 plus 2j, let's call that, I don't know, z1. So this guy is z1 to the 8th power. What's the magnitude of z1 and what's the angle of z1? How do I figure out the magnitude of that guy? Square root of, yeah, so 1 squared plus 2 squared, which is the square root of 5. All right. Which is also, if I wrote that as what's that become if I write that in terms of exponents? 5 to the what? 5 to the 1/2 power. Okay. What about the angle of z1? So before I do angle, I always would think, what quadrant am I in here? 1 plus 2j, what quadrant is that? First. So do I have any problems with arctan there? No, it's good. Right, so what's the arctan of that guy? Imaginary over real, so arctan of 2. I don't know what that is. We can look that up, but it's, I don't know, 30-ish degrees or something. I don't know. So it's arctan of 2. So, I don't know. Somebody calculate that real quick. What is it? 63. Let's call it. Okay. So what do I do here? How do I write this? Z1 to the 8th. Well, I have 5 to the 1/2 power times what? How do I write Z1 here? So I got 5 to the 1/2 power is the magnitude. E to the J, 63 degrees. Again, MATLAB wouldn't like exponential J 63. You'd have to change it to radians. As long as I show that I mean degrees, it's okay though. Raise that to the 8th power. What's that become? What would that become? 5 to the 4th power times what? E to the J, 8 times 63 degrees. Whatever that is. Okay, and then I'd be done. Okay. So I could easily do that in Mat. In fact, MATLAB, I could just say 1 plus 2j raised caret to the 8, and it would be done. All right. But you should be able, again, to be able to calculate it by hand, to know how to go through those things. You need the intuition to be able to do it. All right.
Are you raising the J?
I'm raising e to the power of j times the angle. So it's e to the j times phi. Yeah. E to the j times phi. Right. So if you look at any of my here, like I have exponential j times the angle. Right. All right. Okay. Couple of questions. So it's pretty straightforward. I want to do more with Euler's identity because ultimately I want to make the jump, and I want to say somehow that if I have a general function, a cosine omega t plus phi. Again, I've said, I mean, we're talking about this a lot. I say a cosine omega t plus phi. You're gonna see that in 2112 a lot. Why is that thing important to me? Well, because audio signals are basically cosines. Power signals are cosines, right? Radio signals are cosines. Your cell phone's getting cosines, basically. So anytime I want to analyze any of this, any waveform, usually it's got that form. Okay. All right. So if that's one thing real quick, e to the j, I wrote this differently. E to the j theta, right? Cosine theta plus j sine theta. The only is different is I use theta instead of phi. Okay. Same idea. If I put in a negative theta, why did that change? Right? Why did this change here? Why is there a negative sign here? What's that? Well, it is, but this is positive here. Why is this negative here? This is the general form of it. So if I said e to the j phi equals cosine phi, that's just a definition. We can prove it. we had to. Let's say I said that I plugged in phi is equal to negative theta. Okay, let's say I plug that in there. What would that become? That would become cosine of minus theta plus j times sine of minus theta. What's that become? What's cosine of a negative angle? The trig identity. It's just the cosine of the angle. What happens with the sine? If I have a sine of a negative angle, what do I get? Negative j times the sine of that angle. All right. So I basically use those two results here for a second, right? And what I'm going to do is I'm going to say, well, what happens if I took e to the j theta and I added to it e to the negative j theta, like that? Why would I do that? I don't know, because I wanted to. E to the j theta plus e to the negative j theta. So what does that become? Well, I can substitute these things in here. Cosine theta plus j sine theta, like that. What do I do for the e to the negative j theta? What do I substitute in for this guy? Yep, I add cosine theta and I subtract minus j sine theta. Right? So what's that become? 2 cosine theta. 2 cosine theta. Now, why do I care? Because I said so, right? Because it matters, right? This is actually the thing that makes the jump now between ultimately cosines and the exponentials, right? This is making a link between these two things. Again, which is odd, it's weird, who cares? But what is important about it, it ultimately lets me to simplify a heck of a lot of stuff about how I process these sine waves in a computer. All right? It allows me to start doing DSPs, which ultimately one day gets me to GPUs and all that kind of good stuff, right? So it allows me to do a lot of fancy things computationally that I wouldn't have been able to do otherwise. All right. So what I can say is, in general, cosine of theta is equal to 1/2 of e to the j theta plus e to the negative j theta. Sine of theta, I could do a similar relationship and I can show that to be true. All right. I don't want to spend too much time on that. You can work that out. This is the one that I use most of the time. And we're going to use it a lot as we go. So let's say I've got this guy, 10 cosine e to the 30t plus 10 degrees. And I want to get that into that form. Okay. So I'm going to say that this guy looks like 10 cosine phi. Okay. 10 cosine phi. Sorry, theta. 10 cosine theta. What's theta? Theta is what here? $30t plus 10 degrees. I got to be careful about this. This is really kind of weird, right? If I tell you 30t, tell me what is the frequency in hertz of 30t? You guys should remember how to do that. That multiplier 30 times t. Okay, yeah, he's got it right. So the multiplier 30 times t, what's the 30? What are the units of 30? Angular frequency, which has radians per second as the unit. So radians per second times seconds is radians, right? So 30 is my angular frequency, which is radians per second. What's that equal to? Always equal to 2 pi f. What's f always equal to relative to the period? Yeah, so that's 2 pi over t. So if I figure out the period of that, what would the period be? It would be 2 pi over 30. All right, so that tells me, what's a period tell me? Yeah, how long it takes me to get through one cycle, right? How long it takes me to get through one cycle. One cycle means basically one variation of that cosine wave, right? Also tells me something about these E vectors, which we're going to look at here in a second. So, all right, 10 cosine theta. I want to get that to that complex exponential form. Okay. How would I do that? Well, we said over here cosine theta. Just write down what we know, because this is the very last problem on the homework. Cosine theta is 1/2 e to the j theta plus 1/2 e to the negative j theta. So help me out with that. 10 cosine theta was this guy. I'll put my theta up here. Theta is 30t plus 10 degrees. How do I use this result here to expand out 10 cosine theta? I want to expand it out in terms of exponentials. How do I do it? Yeah. Well, yeah, so 10 divided by 2 gives me 5. Yeah. And then e to the j theta plus 10 divided by 2 e to the minus j theta, like that. Or we can say 5 e to the j theta plus 5 e to the minus j theta. All right, now let's put the theta, let's get rid of the theta, put it in terms of time. All right, so what's that become? 5 e to the j what? 30t plus 10 degrees plus 5 times what? Negative j times 30t plus 10 degrees. Okay. What do I do with that? Well, if I want to break that up a little bit more for myself, right? If I have e to the a plus b, how can I write e to the a plus b? Right, so if I have e to the a plus b, how can I write e to the a plus b? E to the a times e to the b. Okay, and there's a reason why I'm doing this. So I've got that here. I can say that this becomes 5 e to the j 10 degrees times e to the j 30t. All right, what did I do there? What was A and what was B? J10 was my A. J30t was my B. All right. What about this guy over here? What does that become? Let me break it up. I want to break it up a similar way. How would I break up this second term? 5 to the what? E to the negative j 10 degrees times e to the negative j 30t. Like that. Now, why did I break it up that way? Well, again, this is starting to help me think about how I relate these things to complex numbers. Okay. Which is going to be really useful later, because ultimately it turns out if I want to track what this guy is doing, all I really need to know is this value and what that frequency is. And I can get rid of all the time dependence, which is actually useful to me later. We're not going to use that yet, but that's really useful to me later. So look at this guy, 5e to the j10, 5e to the negative j10. What are those two things? We got a term for something like that. One is a what of the other. One is a conjugate of the other. Right? So this guy looks to me like he is, I can also write this as a e to the j 30t plus a conjugate e to the negative j 30t, where a is equal to 5 e to the j 10 degrees. All right, not particularly useful to me, at least not immediately so, but it turns out to be really useful to me. What I want to do is I want to give this some meaning. I'm going to come back to the example I skipped there. But basically, I get cosine and sine. And again, I use the terms interchangeably. I call everything a sine wave, and usually I refer to cosine. You guys have already seen that on the homework. We get, if you have a sine wave, I convert it over to a cosine wave, right? And then we analyze it that way. So I want to think about it like this. If I have cosine omega t. I can think of that thing as, how did I do this? Did it this way, okay. Let's say I have this guy, 4 cosine 1000 t. Using that relationship that I just said, I can write this as 2 e to the j 1000 t plus e plus 2 times e to the negative j 2000 t. All right, now, e to the j 1000 t. That is basically a complex number, right? It's a complex number, and when I say e to the j 1000 t, this guy is a complex number. What's the length of it? Always. What's the length of e to the j 1000 t? 1. What's its angle? Depends on the time. Right? Depends on the time. Okay. So let's take a look at this guy. Because I want to talk, I basically called this guy, I said, I can think of cosine as one vector that rotates forward and one vector that rotates backwards. Now, when I'm talking about rotate, I'm talking about in the complex plane. Okay, so what's it mean to rotate forward? I said counterclockwise, right? Because what's counterclockwise? If I have a complex plane, right? If I'm going this way, that's counterclockwise. Why do I call that positive? Why do I call that positive motion? What's true about angles is I go counterclockwise. They increase, right? That's positive motion. If I go the other way, they decrease, right? So what I'm saying is this thing is like two vectors, two complex numbers that move over time. All right, so we're going to look at this example. 4 cosine 1000 t, I said, is equal to two different things. Let me get back to this, but it's the real part of 4e to the j 1000 t, or it's 2e to the j 1000 t plus 2e to the negative j 1000. All right, let's get back to this real part here for a second. Why did I say it's the real part of that? Why did I say it's the real part of that thing? Why did I say that? What do I know about e to the j 1000 t? It's a complex number. All complex numbers can be thought of as what? Cosine plus j sine. So 4 e to the j 1000 t is 4 cosine 1000 t plus j times 4 sine 1000 t. What's the real part of that? 4 cosine 1000 t. All right, so basically what I'm doing here is I'm kind of showing those three things together at time t equals 0. So at time t equal to 0, 4 cosine 1000 t becomes 4 cosine 0, which is 2e to the j0 plus 2e to the minus j0, or 4. So what I did was I basically showed two things here. I showed what here? Well, there's really three things here. It's hard to tell that, right? What I have on the top is the complex plane. And I've shown basically a set of complex numbers drawn in the complex plane. So what I did was this guy is here and here. Sorry. This guy is actually, he's here. He's here. The summation, this is their sum with a length of 4. All right. It's a little bit tricky, but what's going to happen as time advances? Let's say I get to a time, let's say I get to a time of 524 microseconds. Why I chose that? Because that's part of the period. Okay, 524 microseconds. What's a microsecond? 10 to the what? 10 to the negative 6, right? So 524 times 10 to the negative 6. At that point in time, 1000 t is apparently equal to 30 degrees. So if I use this approach, I have 2e to the j30 plus 2e to the negative j30 is what 4 cosine 30 is equal to. So what is that picture showing here? What's this picture showing here? There's three vectors there. What are the three vectors or three? I say vectors, sometimes I use that interchangeably, vector and complex number, right? Because I draw a complex number in the complex plane, just like I draw a vector. What is that there?
Both numbers conjugate with the other one cancel each other and give you a real.
Yep.
sound.
That's right. So that's the result of basically cosine theta equals 1/2 e to the j theta plus 1/2 e to the negative j theta. I'm seeing that play out here. So which vector is which? I have 2e to the j 30, 2e to the negative j 30. Which one is which? Where's 2e to the j 30? That's this one. That's this one. And then the sum is right here on the real axis, purely real. What's going to happen as time advances even further? Here I did it. So I'm at 1.04272 milliseconds. All right. At that point in time, 1000 t is equal to 60 degrees. So I've got those two vectors again, right? So this is one vector. This is the other. Here's the summation. The summation is always real. What happens if I keep going? Here I am at this time. At that particular time, what's my angle? 90 degrees. So what's going on? One vector points up, one vector points down. What's the sum of a vector going up and a vector going down? In this case, 0, because those lengths are the same, right? So what I'm doing is showing as I keep moving like this, right? So here I am at 0 degrees, 30, 60, 90, negative 90, back to 0 again. What am I plotting out here? So basically, I'm showing how they rotate. At the bottom, I'm showing the real and the imaginary part of the sum, right? The real and the imaginary part of the sum. So what do you notice about the real part there? So what the real part, the summation. So if I look at that picture right there, I got two vectors that have a length 2 that I'm adding together to be a vector that has a length of 4, right? So what I do is I keep tracking that guy. So I added this vector and this vector. This is the real part of that sum. This is the imaginary part of that sum. So what do I see? As time advances, what's happening down here? The real part is tracing out cosine. The imaginary part is tracing out the number 0, right? So what I'm seeing is that a couple of things, right? How I can think of these two vectors that are rotating at the same speed in the plane, always equaling up to a cosine. And those two vectors have no imaginary part to them whatsoever. If I wanted to change the frequency, all this would be the same. What would change if I changed the frequency? Let's say I increased from 1000 t to 2000 t. What would change? Anything? Just how fast it's rotating, right? So basically, what it turns out is if I can think of cosines in terms of these two vectors that are rotating around, turns out I can simplify a heck of a lot of the computations I need to do. Now, your brain is fried for the moment because we've been doing this for an hour and 15 minutes. But it'll be fried because I'm dealing with imaginary numbers. But the imaginary numbers ultimately make a lot of the calculus a heck of a lot easier. All right, and a lot of the processing a heck of a lot easier. Question?
So if you have a sine function here, you see the opposite.
If I had a sine function, I would see something a little bit different. I want to go back to that question real quick because I know you guys are going to ask that later. Let's say I did this guy, 10 sine 30t plus 10 degrees. What I would do with this is I would convert that to an equivalent cosine right off the bat. So how do I get sine and turn it to a cosine? I can always go back to my trig identities and figure out what the relationship is. The way I think of this in my head, right? As I say, sine looks like this, cosine looks like that. So what did I have to do to cosine to get to sine? I had to pull cosine that way 90 degrees. So if I had to pull cosine that way 90 degrees, do I add or subtract 90? Subtract. So this becomes 10 cosine 30t plus 10 degrees minus 90 degrees. Right? That's always the way that you end up doing it. then I would just approach this just like I did before. Right? So I would end up with 5 cosine j 80 degrees times e to the j, whoop, not cosine. What am I doing? Trying to do too much. E to the negative j 80 times e to the j 30t plus 5 e to the j 80 e to the negative j 30t. All right, you got one problem like this on the homework that asks you to blow up some of these things like so. All right, and then you're gonna have a lot of that probably on the next one. All right. So anyway, you're gonna get used to this. We do that. I start here with the class, and then we use it all throughout. All right. So that's it for today. I will say again, I will be on Discord. You know, you guys have